So, well, what is a spherical polygon? It was already mentioned in the previous talk that we have a disk with a metric of curvature 1. There are points on the boundary which are called corners. So at the corners there are conical singularities, and the sides are geodesics of the metric. So it must remind you that there is a tradition to measure the corners not in radians but in half turns. So when I say integer angle, means it's integer multiple of pi for a polygon. So when again the metric of with conical singularities on the sphere, which was again the subject of the previous talk, is a more general case, and if the metric is symmetric with respect to the real axis, and all the singularities are on the real axis, then we can cut it down, our sphere down into halves, and each half becomes a spherical polygon. So there is an excellent review by Alex that in particular the easiest way is to find it on his website, and about all history and numerous ramifications of this spherical metrics and polygons. So here are some examples of simple, like triangles. A and B are spherical triangles, and C and D are spherical quadrilaterals. These are small ones. The main difficulty here is that these small ones just belong to the sphere, and that's easy to understand them. But in general, the sides are very long and the corners are very large, and the disk, which is our spherical polygon, in particular quadrilateral, does not fit into sphere. It's a spread over sphere, covering it many, many times. So that's why the problem becomes more interesting. So what are classification problems? Of course, first of all, we would like to have existence. What are the conditions on the angles for which such a metric exists? And the conditions were found for the general case in Mandela-Panov, and Alex completed it with all. Well, what was missing was the cases with commutative monodromy group. So that was done by Alex, and in general, the Gauss-Bonnet theorem gives inequality. The distance to the odd integer lattice, odd means the sum of the components are odd, should be greater or equal than 1, and the distance again is d1. So that's at least existence is understood. Then the next question is how many spherical polygons with the given angles and corners may exist. This question is not completely answered, well, at least for the quadrilaterals with at least one integer corner. We have a Bizu theorem. For the general case, there is some finiteness that again proved by Alex, but in general case, it's still upper and lower bounds. Well, there are some lower bounds, but then not clear whether they're good or not. And finally, if you start with triangles, well, there are digons which are more or less trivial case. The triangles were classified by Klein, who used them to study hypergeometric equation, and there is a simple inequality on the angle that guarantees existence, and the triangle is always unique. It's completely determined by the angles. And Klein did generic cases, and non-generic cases actually its uniqueness is not true, but pretty much understood, and that was done by Alex 2004, a little bit corrected. So even for triangles, and Dmitry mentioned in the previous talk that the space of all spherical triangles has a very complicated structure, and it was only recently more or less completely understood. So even for triangles, the story is well, going on and on. There are more and more questions that are answered again. So and then we are coming to the quadrilaterals, the next case, and I would say in advance that for pentagons, there's practically nothing known except what I mentioned. There is a paper about special pentagons, which are well, not much different from quadrilaterals, and they are related to the Penlever-6 equation. But for quadrilaterals, there is again a long story. When the angles are small, then there is existence of uniqueness conditions. But in general, for large angles, the larger are the angles, the more non-uniqueness shows up. And first of all, if the angles are all integer, remind you that integer means integer multiples of pi, then it's actually equation about rational functions, and it was related to Shapiro and Shapiro conjecture in case of two polynomials, which we solved with Alex in 2002. And next, well, you cannot have one non-integer angle because of monodromy. The sum of monodromies should be trivial, so one cannot be. But if you have two integer and two non-integer angles, then it is in our paper, Alex and Tarasov in 2014. And the next case is when there is one integer and three non-integer angles. That again, it is the same authors in 2016. And then there is a very interesting special case, spherical rectangles. So all angles are odd multiples of 1/2. So in this case, you cannot have the four sides on four circles. In fact, two opposite sides must be on the same circle. Otherwise, such a rectangle does not exist. And so there are three circles. And that was in our paper with Alex in 2016, in which already something happened, which never happens with integer, with the presence of an integer angle. And finally, if all angles are non-integer and sides mapped to four distinct circles, then it is my paper on 2022, which I would consider Alex to be a co-author, and I suggested him to be a co-author, but he refused, unfortunately, because his original question and his our communications during these many years, definitely without those, I would never finish this. And this is the subject of today's talk. So, how you approach this problem? Well, development map already was explained in previous talk. So you have a metric of constant curvature 1, which means locally your surface is like a small piece of a sphere. And so you can extend it by isometry to mapping from our disk to the whole sphere. We usually use the upper half plane as a conformal version of a disk. And then you have the marked point on the boundary is the real line, and the marked points correspond to the corner. And you have this mapping from the upper half plane to the sphere, where our upper half plane, again, in this case, it's a simple quadrilateral. It is embedded in the sphere. In general, when your angles become larger, it will self overlap, and it just will be spread over sphere. And the intervals, the sides are intervals between the corners are mapped. Forgot that I can. Oh yeah. So the sides are mapped to the arcs of great circles in the sphere, and the great circles have combinatorially unique configurations. The four great circles have combinatorially unique configuration that is shown in this picture. So let me see that. So how we approach this? There is a combinatorial invariant and continuous real invariant of classification. So first of all, we have this great circles. So we have four great circles in the sphere. We assume that's a generic. So those great circles are distinct and transversal. Moreover, at the moment we assume that there are no triple intersections. So if you just take a pre-image of those four circles, we have a certain graph inside of our quadrilateral, and or in general, well, if you have a polygon, there are more circles, but it's beyond this talk. So in quadrilateral, we have cell decomposition of the disk. It is called net. The the name goes back to some middle of the 20th century, and it was used in our paper with Alex on the case of rational function for Shapiro conjecture. So, well, the net is a geometric object, of course, but we consider it up to a homeomorphism. So we say that two nets are equivalent if they can be mapped to each other by the orientation preserver homeomorphism of the disk, respecting the labels of the corners. The corners have fixed labels; they're numbered from 0 to 3. And after that, the equivalence class is a combinatorial object. So we consider nets as combinatorial invariants of our quadrilateral. And to define it, we have up to isometry, of course, we have to define its net, which is combinatorial. We have to define partition of S by 4 great circles, which is actually not unique, happens. And the images of the corners. So we can map the development maps, sends the corners to some intersections of our circles, and in general, there may be different images of this that would give you different quadrilaterals. So, so here are the two pictures. In fact, it's the same configuration of 4 great circle, just with different projections. The 4 great circles partition the sphere into several quadrilaterals, like here A, B, C, D is a quadrilateral, and so that's one. And the same quadrilateral ABCD is on the other. So the two pictures are just projections of the same partition. And several triangles. So here the triangle, like infinity in a triangle. Here the infinity is in quadrilateral. But it has a very simple structure. Every quadrilateral is adjacent to 4 triangles. Every triangle is adjacent to 3 quadrilaterals. So it's a very simple and very symmetric, combinatorially symmetric decomposition of the sphere, right? Great circle. And but there is more. When you have 4 circles, there are not 4 but 6 angles between them. And we have a quadrilateral with 4 fixed angles at the corners. And so this means that 4 of those 6 corners are fixed and the other 2 are not. So, so I assume here that A, B, C, and D are fixed or there. There is always, again, when you have 4 fixed corners, there is always a quadrilateral side, a quadrilateral face of this partition, such that all 4 corners are actually angles of this face. Like this face here and this face here have fixed corners, I assume. And then there are other 2, like E and Z, which actually goes back to epsilon and zeta that will appear later. And these are not fixed. So you can deform your configuration without changing A, B, C, and D, except there is a relation between these 2 corners. So in fact, like if one corner increases, the other of them decreases, so that there is an algebraic relation between the trig functions of those corners, and in fact we only have one parameter, free. So this decomposition of a sphere is it's unique combinatorially, but metrically it's one parametric. It's an interval of four circle configurations. And to start the composition, the classification, there are several what I call basic quadrilaterals that are shown here. So, well, forget about notations. Notations have a long history and are not that much relevant. But the key point that two of them. Let's see. Okay, so this is the simplest, just a single phase. These two are symmetric, reflection symmetric to each other, but because we fix orientation, it's not exactly the same. And and the third one has two. Here all four angles are simple, less than one. These are here you have three angles less than one, and here we have two angles less than one. So these are essentially the seeds from which grow all the other combinatorially grow all the other quadrilaterals. So and here are here they are shown as subsets of a sphere, and these are corresponding nets. So if you when we replace a quadrilateral by the nets, we forget about the metric or geometry. We just consider combinatorics. Like here we have two circles crossing this quadrilateral. So these are two segments of the net. So the net is just combinatorics. And what we can do to get more complicated quadrilaterals, there are several operations. First of all, you can extend the sides. I think actually I had this. Yes. So there are several operations that we can do. Extending the sides. There are several figures that will show how it is done and what the result. Sometimes you have extend one side, sometimes you have both sides. Then there is something which is called pseudo-diagonal. I'll tell about it more. There are no diagonals, but there are pseudo-diagonals later. And then there is attaching disks to short sides. So when a side is less than the whole circle, you can think of it as an arc of a disk. You attach a disk at this point. Your angle is two angles are increased by one, and then you can do it again and again. The remaining part of the boundary of the disk is again short side. You can attach any number of disks you like, and that's also but that's a simple kind of operation. Although there are some subtleties about that, but it's essentially the simplest part of the whole story. So here are examples how you could attach, extend a side. Like in the gray area, here is the original quadrilateral. This is what is called P sub 0. It's in all pictures, it's the same quadrilateral, but here we have a side extended. Here it is. There are two adjacent sides extended. Here is one side extended in two ways, and here are two opposite sides extended, again in different ways up to reflection, but again, since we keep orientation, reflection is just this bar. So these are reflection symmetric, but not isometric with orientation. And here is more extension when you start with a different. So here you start with this quadrilateral. Again, it's in all pictures, it's the same quadrilateral, which was called X prime 0, 0 for some reasons. And we extend one side with here, and that's again symmetric, reflection symmetric there. And then we can extend, so this is the side which is opposite to there is one corner which is greater than 1. So here we extend a side which is opposite to this corner. Here we extend the side which is adjacent to this corner. And here's again another way to extend the side. So this way we obtain combinatorially different quadrilaterals. There are a few cases where you actually get the same quadrilateral with two different operations, and they're easily controllable, so it's not a big deal. So here we have again the same quadrilateral in the interior, but now we extend two sides. Like here there are two adjacent sides, here we have two opposite sides, and here is the extension of the same side but in two directions. And again we have different combinatorially different quadrilaterals, but the basic quadrilateral is the same. And this is our last basic quadrilateral, Z, which is which has only two non-integer angles. So here both angles up and down are greater than 1. So these the only two angles smaller than 1. And again, you may extend one side this way, that way, which is symmetric, and or you can extend both sides which are adjacent to these angles, or you can extend opposite sides which are both adjacent to the angles which are greater than 1. So there are already at this stage you can see that the classification is ramified pretty much. So we have essentially 3 basic, because 2 of them are reflection symmetric, and then there is still pretty much easily understood way to extend the sides, but already produces a bunch of non-equivalent, combinatorially non-equivalent objects. And now the what is called a pseudo-diagonal. So first of all, you cannot have an actual diagonal, an arc of a net connecting two opposite corners, because in two opposite corners, in one corner we have like black and blue circles, and another corner we have red and green. So any arc would require the same. An arc has its own color, so it cannot go from one corner to the opposite corner. So there are no diagonals in our quadrilaterals of the net. But there is something that I call pseudo-diagonal, and it looks like something sophisticated. But what happens here, in fact, is that you start with a simple quadrilateral with anything inside, empty. And then you make a cut between two corners, which is not shown here, and glue in a complete sphere inside this cut, and you extend your quadrilateral by adding a complete sphere in the middle. So what is this pseudo-diagonal? It's actually part of the configuration. So if you look at, like, drop one of the corner points like this, then all the rest would be exactly combinatorially a net of a four-circle configuration of a sphere. So what we have here, we started with an empty net and essentially added to it a full sphere. And moreover, after we added one full sphere, we have again a face which is a quadrilateral, empty quadrilateral with two opposite corners. So we can add another sphere. And again, so you can insert any number of spheres this way. So any number of pseudo-diagonals can be inserted. And that's another parameter of combinatorial classification, how many pseudo-diagonals you have in your quadrilateral. So, so these three operations give a pretty sophisticated classification, which I'm not even going to show because it wouldn't fit into the screen. But well, essentially, there are three ways you produce this classification. Yeah, and moreover, I didn't show what happens when you add the disks to the boundary. So after this extension of the sides and adding pseudo-diagonals, like in this picture, you have four short sides. So to each side, you can attach as many disks as you like. It will be again a spherical quadrilateral. You just add one to two adjacent corners, angles, attaching any disk, and that's a simple operation. So I'll skip that. So far it was all combinatorics, but now we are getting back to our four-circle configuration, and remember that we have two angles which are not fixed. Well, in this picture, E and Z are angles which are not fixed, and A, B, C, D are fixed. So there is a face which is marked by F, of which A, B, C, and D are the angles at the corner. So all four angles of this face are fixed. There are actually two such faces. There is one which is called F, and another one you can see is the outside, the face that contains infinity. It also has A, B, C, D, but in the opposite order. So because the two angles are not fixed, but there is a relation between them, there is only one parameter. you can move one angle increase, then another angle decreases. And that gives you an interval, one-dimensional interval in the space of configurations, of four-circle configurations. And correspondingly, if you fixed the net, which is then this family of configurations gives you a family of quadrilaterals. So you fix the net gamma and fix four angles, and then you have I sub gamma, which is an interval in the space of all quadrilaterals, which is parameterized by, you can choose any of the two non-fixed angles. It will parameterize this interval 1 to 1. So this actually are the angles. So quadrilateral has fixed angles between its adjacent sides, and the opposite side, the angles between the opposite sides are not fixed, but they're related. Now, with a fixed net and fixed four-circle configuration, we have a point on this interval, and then we have this open interval. Now, what happens at the end of this interval? So it may happen that our quadrilateral at the end, when we get to the end of the interval, degenerate, like one side or contracts, or some internal, like two opposite sides come together at some point. So it may become a triangle, or it may become something else, but not a quadrilateral. That's what means conformally degenerate. Then it may happen that it converges to non-generic spherical quadrilateral, but the four-circle configuration is not generic. It has a triple intersection. And that's a good case, because in this case, we can extend, we get to this non-generic case with triple intersection, we can continue our deformation through the triple intersection, and we'll get another generic configuration and another generic quadrilateral, but with a different net. And there is a bad case. Well, this conformally degenerate, like the good, the bad, and the ugly. So conformally degenerate is ugly. The triple intersection is good. And there is a very interesting case that was called, I think, in Mandel and Panov, because Lin Wang boundary. So we are getting to a quadrilateral, still a quadrilateral, but to understand conformally that is quadrilateral, we have to make a special family of conformal transformations. That as a result, our limiting quadrilateral is not spherical anymore. We cannot get back. So after conformal transformation, our quadrilateral becomes non-spherical, becomes circular but equivalent to a spherical. But there is a case when the limiting quadrilateral may be non-spherical, completely not equivalent to any spherical. So that's the bad case, but not that bad. So that means you when you get to it, you still have a quadrilateral with non-trivial modulus, but you cannot get through, because on the other side there is nothing spherical. So now suppose that we have in a good case, so we have a net of gamma minus and gamma plus, and two intervals have a common end. with a non-generic quadrilateral, but decent spherical quadrilateral of non-generic spherical configuration, then you say that it belongs to a chain of quadrilaterals, and then nets belong to a chain of nets. So we can glue these intervals together, adding this non-generic one, and then we can continue until we get to some of the bad cases. So what? So you have a conformal modulus. That's, I already mentioned that there is conformal degeneration. It's all about conformal modulus. So we can map our quadrilateral onto a rectangle that so that corners are mapped to the corners, but now it is a just metric rectangle with in the complex plane, two sides on the axis and to other sides parallel to the axis, and the and the conformal modulus is the measures the difference between this rectangle and a square. So it may be thin, low and long, or maybe high and thin, and that what this modulus k goes from 0 to infinity. And when I say conformally degenerate, means that you have a family where in the limit k goes to 0 or to infinity. So if you have a chain of quadrilaterals, so we have a sequence of intervals of spherical quadrilaterals where at the common ends, again, it's non-degenerate quadrilaterals, then this conformal modulus at the end maybe 0 or infinity, not in a random way. Like if you have just one interval and at the one end is 0, then on the other end it must be infinity. If you have two intervals, then and one end 0 and the other end also 0. So when we go along the chain and pass each of the intervals, we have a single option how our quadrilateral may degenerate. So if the chain contains even number of nets, then the value of the modulus at the end in the limit would be the same, or 0 at both ends or infinity at both ends. And if the number is odd, then we must have 0 at one end and infinity at another end. In particular, that means that our family passes all the way from 0 to infinity in the modulus. Of course, it may wiggle on the way, but this gives you actually a lower bound on existence. So if you have a chain with odd number of intervals, you are guaranteed that within this chain, there is at least one quadrilateral for every value of the modulus. So if you ask whether a quadrilateral exists for, and how many quadrilaterals exist for given angles and for given value of the modulus, then every odd chain gives you at least one, sometimes more. So the chain with odd number of nets contains quadrilaterals with any conformal modulus, well, unless it has a degeneration to a quadruple intersection, which is the bad case. So let me show you what how this bad case appears. Oh no, that's a good. Okay, this slide is a good case. So the good case is that we have 4 circles, see 4, and where the sides are mapped, and we number them in the same order as the sides of our quadrilateral Q. And so we have 4 fixed angles, and then strictly speaking, angles between the circles are defined up to a complement. So, but you have given a configuration, there is always a quadrilateral face of a configuration of 4 circles where all our fixed angles are actually the angle of this configuration. By the way, they're related to the fractional parts of the angles of our quadrilateral, but they may be equal or opposite to the fractional parts. So it's not exactly the same. So, and this inequality, of course, it's yeah. First of all, the angles of such a face are between 0 and 1, and then there is the relation that actually which says that there is a diagon that contains our face, and that gives you another relation which actually goes from also Gauss-Bonnet. So there are 2, as I mentioned, angles which are not fixed, they're related, and each of them may be taken as a parameter on this interval. And moreover, if one of them increases, the other one decreases. So when the 4-circle configuration is deformed, these 2 angles are changing in the opposite direction. So here is the picture that what happens. You start with a non-degenerate configuration like in the middle, and you fix the face F, which is now also in the middle, where A, B, C, D are the fixed angles. And then you can move up or down, left or right. And what happens is at the end, you get a triple intersection. And the color of the arrow actually corresponds to, there's one circle that is not in the triple intersection. So this blue arrow means the triple intersection of 3 circles except the blue, and so on. So there are, in general, 4 ways you can deform your 4-circle configuration to a triple intersection. And in fact, well, for configuration, all 4 are possible, but if you want also the quadrilateral to move, there are only 2 of them. So it's like so there are 4 triangular faces. The areas of the faces are well easier as usual on the sphere, simple functions of the angles, and once deformed, the top and bottom angles are changing with the same rate, and left and right angles are changing with the same but the opposite rate. So depending on whether top and bottom areas which are equal are smaller or larger than left and right. Only one possibility happens, whether you can go up, like up or down, or left or right. It all determined by the smallest area or correspondingly smallest angle. So that's exactly the rule. So if like A plus B greater than C plus D, then configuration be deformed to a triple intersection with top and bottom, or if A plus B greater than, then you can put go to the bottom and then A plus D greater than B plus C, then you can only go to the left or only to the right. So if you have just no equal angles out of these four, then you can only allow it to give in one direction, either up or down, and only in one direction, either left or right. And then when you arrived in this triple intersection, you can go beyond, and you have quadrilateral with the same angles, but with a different configuration and different nets. When you pass the triple intersection, the nets. So here, what is shown, what happens when you pass the triple intersection. Again, the colors of the arrows mean, like this blue arrow means that you are passing through a triple intersection where the blue circle doesn't belong. So only red, green, and black pass. So blue circle remains, but you see that here we had A and D, and red, green, and black. And here we have A and D exchanged after we passed triple intersection. So we have different now. What we are always looking at is the quadrilateral face where all four corners are fixed. And now A, B, C, D, our quadrilateral face is here. So it was here, but now it is there. And similarly, when you go down or go up, you have again a generic configuration, but the set of circles where the face where the angles are fixed is different. Because of that, you get a different net. So these are examples. What happens? So we are looking at the net. In general, we have the except in the corners, we have the net has like single points on the sides. But when we pass through a triple intersection, we have this triple intersection. So there are three colors appear in the same side. So, and then letters means that here we from the net classified as R pass to a net classified as S, and here we have from net classified as V classified as W, and here from U to V, and here we get from X to X, but with the different parameters. Again from Z. So these are like special kinds of nets And notice that sometimes this bad point, like here, the bad point is actually at the corner, and here it's in the corner. Sometimes the face where we need is outside the net. You don't see it in the net. But again, it is in charge of the classification. Okay, and the last, maybe the most interesting case, we first encountered it with Alex in the paper on spherical rectangles. So here we have a nice configuration of 4 circles. And then we deform, and it happens that these two areas are equal. So we deform contracts in these two areas, up and down. And in the end, we get what is B. So we have, of course, if we keep it isometric, then all 4 circles would collide into one. But we can make a conformal transformation so that they remain distinct, but get to quadruple intersection at 2 points. But we have more freedom in conformal transformations. In particular, we can make a family such that this part is all contracted to a point, but this we keep away from a point, so this part is not contracted. And that's what is case C here. So all our A, B, and the other 2 points are now contracted to the same point, point in the limit, but the other 2 not. Not that it's definitely not at all configuration of great circles. These are not great circles. Well, at least so some of them are not great circles. And but it may happen. Okay, so yeah. So because we have a quadruple intersection, we can send it to infinity, and our configuration becomes actually Euclidean. Instead of 4 circles, we get 4 lines. Now our quadruple intersections is infinity, so we have just 4 lines. So in this case, in the limit, what we actually get is a Euclidean configuration. And here's an example how it may happen with an actual quadrilateral. So here in A we have a nice spherical quadrilateral. It's actually small, so it belongs to a sphere. You don't have to deal with the large objects which are not covering the sphere. So we go to B, where we've got a triple intersection here and also triple intersection here. Then we make a transformation. We go to C, which is again. So here we have a triple intersection. So everything is fine. We pass the triple intersection. We get a different net. So pass another triple intersection and get a different net. And then it is easy to show that if you try to go beyond here or beyond here, our quadrilateral would degenerate. So that's an example of a chain. So this is a good case. We started somewhere in the degenerate quadrilateral, which is not shown. This is a one-dimensional interval. This is the triple intersection, one-dimensional interval, triple intersection, one-dimensional interval. And this is another example when we actually get to the quadruple intersection. So again, we start with this one, which is nice, non-degenerate. On the other side, if you try to go to the other side, it will degenerate. If you go this side, after conformal transformations, we get a non-degenerate quadrilateral, but that's not spherical. And that's a boundary. That's a boundary which is non-degenerate, but you cannot pass it within spherical quadrilateral. We must go beyond spherical quadrilaterals. And that's, I believe, yes. So I'm out of time. So about Fuchsian differential equations, you already heard. And let me stop here. And happy birthday, Alex.
Any questions? Or any comments?
Could you show me the statement of your main results? So,
Which one?
which is the main statement?
So sorry. Which which statement?
I want the main theorem. What is the main theorem?
Oh, the main theorem, the main theorem to formulate it would take several pages. So the main theorem is that for suppose we have fixed angles of spherical quadrilaterals, fixed four angles, then first of all, there is a non-uniqueness and such quadrilaterals. There is a corresponding circle configuration, four great circles on the sphere, and there's in fact one parametric family of such configurations, or circle configurations. So our quadrilateral has a net, which is a pre-image of these four circles in this quadrilateral up to homeomorphism. So it's a combinatorial invariant of our quadrilateral. So first of all quadrilaterals are classified combinatorially by their nets. And that's purely combinatorial part of it. And already this classification is it is explicit, but pretty complicated. But then within each combinatorial class, suppose we fix now angles and we fix a net. Then the statement is that first of all, this net, this gives you an open interval in the space of quadrilaterals, which at the end of this interval, there are three possibilities, depending again on the angles and on the net. The quadrilateral may conformally degenerate, and that means you stop. Your modulus become 0 or infinity, and you can go not further. Or your configuration becomes non-generic. Your four-circle configuration get a triple intersection. Then you can pass through this triple intersection and get another interval, and so on until you degenerate. Or if you have some equality on this equality relation between the angles, you may get to a quadruple intersection. So instead of triple intersection in the limit, you may get a quadruple intersection. In this case, again, it may happen that your quadrilateral does degenerate in this quadruple intersection, so it's you are still at the limit k equals 0 or k equals infinity, or there are examples, and again, you can check in which cases this may happen when in the limit the modulus does not go to 0 or infinity, and so if you do conformal transformation, which modulus is invariant, you get a quadrilateral with a quadruple intersection, but it's not spherical, it's circular. There is no equivalent. Any spherical quadrilateral is equivalent to infinitely many circulars. We can always make conformal transformations of your sphere, but that's the third possibility is that you get to this boundary where your limit quadrilateral is non-degenerate, but is not spherical, and you cannot pass this boundary. So in the space of quadrilateral, there is a very strange boundary, and I think it was called Lin-Wang boundary by Mandel and Panov, because it was again discovered also by Lin-Wang, and we discovered it with Alex when we studied rectangles first. It never happens when you have at least one integer angle, but when you have all non-integer angles, this happens. And these are all possibilities. So the whole space of spherical quadrilaterals consists of a bunch of these intervals that correspond to at the ends. They may go from 0 to infinity. They may go from 0 and get back to 0. They may go from infinity back to infinity, or you can go from 0 and stop somewhere in the middle. In the this boundary where you cannot get through with a spherical quadrilateral. So that's the statement, but it's not a simple statement. The classification is it was not by chance that I spent so many years until it was completed. It's definitely not a high school geometry problem. What I also want to mention, in general, there is a relatively simple case of this classification. Suppose that our quadrilateral has only one big angle. So one angle is greater than one, and the three other angles are less than one. Then there is a single kind of a net. So combinatorial classification is very simple. It's essentially just one parameter. Well, again, there are two one-parametric families, strictly speaking, and this distribution, the list of the nets also, again, in my paper, the end of this paper shows explicitly what happens when you have only one big angle. And these are examples. Each of these examples takes several pages. So that's the simplest case. So that's unfortunately the nature of this problem. The answer is very complicated, and even the simplest case, well, of course, when all the angles are small, easy, there is uniqueness. But even if one angle is large and three angles are small, it's already, and the worst case, yeah, we have several papers with classification of quadrilaterals which have at least one integer angle. In all those cases, when there is at least one integer angle, the development map, the relation with models is algebraic. So there is a Bezout theorem, there is a nice upper bound, and there is no bad case. These things never happen. But As soon as you have no integer angles, classification is very complicated, and you have these things that are still not properly understood.
Any more questions? Yes.
Maybe just a very quick one, hopefully. So how should we think of the space of like all quadrilaterals? Is it right that like if you have at least if you have a generic one, it's like a manifold which is foliated by these curves, or is it even more complicated than that?
Yes, so the space of all quadrilaterals with a fixed angle, with fixed four angles.
No, but I want to change. I want to think now what happens when you change.
Oh, when you change the angles. Oh, that's a very good question. Even for the triangles that was in the previous, there is a separate paper of Alex and myself that describes, of course, Mondelo and Panov did this classification first, and then we tried to describe topology of this. And even for triangles, it's a mess. There are blow-ups at many points. Well, like you saw
it's
those
complicated.
octahedrons that join at vertices, but actually at those vertices there is a blow-up. It's not a single point. It's a bunch of triangles. So here it's even worse.
Okay, thank you.
So moreover, it's an absolutely open question. What happens when you approach like integer angle from non-integer? We have no idea. Well, what we know that when you have quadrilaterals with at least one integer angles, nothing happens. You see, it's an algebraic curve that passes through this integer angle without any singularities. So it looks like it should be very simple, although from the point of view of quadrilaterals, it's an ugly degeneration. But for generic case, we have no idea.
Any more comments? Perhaps I can say something. So in the beginning, Andrei told us that the problem was suggested by Alex. And if Alex can hear me now, I was just wondering if I can ask whether he accepts this solution. Hello.
Alex, can you hear me?
Yes, I do, but I didn't hear the question.
The question is, did I answer your 15 years ago? You asked me a question. Did I answer it, or it's still not?
Well, you answered it, but it is much more complicated than I expected. The answer is much more complicated than I expected. So I was hoping for some neatly stated theorem, but it turns out that there is no neatly stated theorem here. It's a very complicated classification. However, parts of it can be used in some cases which one can grasp by intuition, and so I am kind of unhappy of the complexity of this thing, but it is well, it seems to be in the nature of things, unless someone discovers some neat formulation. I don't know. Well, this can be compared with this old German thesis. So the first attempt to classify even not spherical but circular quadrilaterals, which is a bigger class. It is due to a student of Klein who wrote a huge thesis on it, and it was a kind of starting point for us to trying to understand this, at least in the special case of spherical quadrilaterals, and this is what we came out with, which is even more complicated than that original thesis, unfortunately.
I hope this is a solution at least accepted as a birthday present. Right, so let us thank the organizers for bringing. Shall we pass it to lunch?
So maybe just, very briefly, well, I said yesterday already to thank David and